about resistivity surveying in karst terrain and how moisture affects the results. A geophysical survey was conducted in 2016 at an existing fly ash landfill in southwestern Missouri as a part of the stability demonstration in accordance with the new EPA's rule on the coal combustion residual that was published in 2015. The goal of investigation was to determine if the landfill and surrounding areas were underlain by karst features that could potentially compromise the integrity of the structure of this landfill site. Here a little bit of information about geology of the state. So much of the state is underlain by carbonate rock that has the potential for karst development. When water moves through soil, it becomes acidic from decaying organic material, then it seeps through fractures and joints in limestone and dolomite and slowly dissolves the rock. Through this process, solution widening joints, caves, and caverns develop in the subsurface. As the rock removed, the soils above, especially the ones composed of fine particles such as clays or silts, wash into the void space, and with time, sinkholes develop at the surface. Karst terrain in Missouri is often characterized by highly variable depth to top of rock, and it is an important parameter in a variety of engineering fields. So, for example, shallow bedrock may limit subsurface infiltration and affect utility services. At the same time, deeper bedrock may not support the weight of a built structure unless the soil is removed or modified somehow. In terms of groundwater, knowledge of flow pattern is essential for effective contamination control. There are approximately 16,000 mapped sinkholes in Missouri, and of course, many more exist and just haven't been reported or documented. And the largest sinkhole is approximately 700 acres, or about 2.8 square kilometers. Missouri is also home to more than 7,300 caves, making the state second to only Tennessee. And also we have the Big Spring, which is one of the largest in the country and actually in the world, with the average depth of 12 cubic meters per second. So on the right side, there's a column, and the geology here at the study site is presented by Burlington Kirkuk limestone, and this limestone in parts of the Reed Spring Formation in the southwestern part of the state are hosted deposits of zinc and galena ores. It's also used as architectural and decorative stone. The exterior and the interior of the Missouri State Capitol, for example, that was built about 100 years ago, were built with limestone that was worked in the same area where the study site is. So nevertheless, Burlington Kirkuk limestone is prone to karst because it's limestone, and it's important to understand the subsurface conditions for structure stability, such as a fly ash landfill. And here are some photographs from Missouri. In the first one, photograph A, the sinkhole developed early in the morning on a summer day in 2006. And a gentleman was inside of the house when this happened. He has heard the cracking noise, and he opened a door to his garage and found that half of his garage was gone. He was safely evacuated, but 2 hours later, the entire garage and part of the home, along with the vehicle in the garage, were swallowed by this 75 deep or 23-meter deep sinkhole. So nobody was hurt, but obviously the house was lost. And this was about 15 miles, 24 kilometers away from the study site to southeast. In figure B, karst development process is depicted. As discussed earlier, water seeps through acidic soil, becomes slightly acidic as well, and seeps into the fracture and joints in carbonate rock. And then this rock is dissolved over time, and the fractures become wider, and over time may lead to a sinkhole development or other karst feature development. In C is a photograph of the Burlington Keokuk limestone. Basically, that's the limestone we're dealing with at the site. And you can notice the near vertical fractures or joint sets that are as wide as 10 centimeters. So most of the fractures and joint sets are near vertical in this particular unit. D shows a drone a photograph, and there's a sinkhole in close proximity to the study site. And this round shaped classical sinkhole actually becomes a little pond in the wet season. And many farmers use the sinkholes for livestock. And in figure E, uh, there's a photograph from a golf course, also in Missouri. It's about 55 miles or 90 kilometers south of the study site. Several sinkholes developed within a week or so, right on the turf. And it's interesting to note that this event of developing sinkholes attracted more tourists than the actual golf. There's a known cave in the area, and the owner wanted to do exploration of these sinkholes and see if these features are connected to the cave. And cave is open to tourists. So he thought it'd be nice to have access to the cave right from the lodge or from the restaurant. Uh, we were lucky to participate in this survey. We acquired resistivity data. You can see yellow cables laid out on the grass on the right side. But we didn't find the connection between the sinkholes and uh, the existing cave. So the owner, instead of remediating the sinkholes, he decided to do something different, and he excavated them, and it became an attraction on its own. It's kind of cool to see what we have to deal with in karst terrain when the soil is removed. So it's pretty impressive. This rather extreme karst, but we have a lot of places in Missouri that have subsurface conditions like this. Bedrock in the study area is characterized by two nearly orthogonal joint sets that exhibit general strike orientation approximately northwest southeast and have vertical dipping. There are some known karst features in the area, such as depressions and sinkholes in close proximity to the study area. The approximate locations are shown here in yellow, green, and blue. And it's interesting to note that these mapped features appear to fall on some sort of lineaments that are consistent with the orientation of the preferential joint sets at the site. So southwest northeast, northwest southeast. And from our experience dealing with the sinkholes and karst terrain, first of all, using the geophysical techniques, it's not uncommon for many sinkholes to develop at the intersection of solution widening joints. Sometimes it's two joints, sometimes it's three or more. Here's the site. Uh, it's a fly ash deposit site from operating a coal-fired plant to produce electricity. This particular facility, they have a couple of plants, but they supply energy to about 110,000 people. And this facility was developed in the early 80s. It was extensively drilled at that time to determine depth to bedrock and the number of soil trenches. Were excavated to the bedrock to make sure that the soil is characterized and the nature of the bedrock surface is understood. At that time, the site was determined to be suitable for development of the fly ash deposit and was permitted and constructed in the mid 80s. The landfill was constructed in accordance with the Missouri Department of Natural Resources requirements that existed at that time. By the time of the geophysical survey in 2016, the landfill received about 1.5 million cubic yards or 1.1 million cubic meters of the deposits since its opening over 30 years ago. The one type of karst feature which has potential to compromise the integrity of structures is cover collapse sinkhole. This type of sinkholes originate in the soil bedrock interface when soil is eroded into underlying bedrock solution cavities, and the resulting soil void can propagate upward until it becomes a surface collapse, or in case with the CCR landfills, unit can undermine the structural support of the landfill components, such as a liner. Electrical resistivity tomography or ERT, coupled with multi-channel analysis of surface waves or MSW, was selected as a tool to investigate karst features, if any present in this location, including the cover collapsing holes. Um, this combination of ERT and MSW um, has proven to be a very effective means to identify and characterize these features. So we use this combination in karst terrain a lot. ERT is a non-invasive imaging method designed to measure variations in um, resistivity of soil and rock. You can acquire data in 1D, 2D, or 3D. Most of the time, data are acquired in a 2D mode because it gives you better coverage and not as expensive as 3D. Uh, ERT data were acquired along parallel traverses oriented south-north and spaced approximately 6 meters apart. We used dipole-dipole array, and up to 168 electrodes were used at spacings of 1.5 meter or so. Here's the slide on the electrical resistivity imaging method. The whole idea is based on the Ohm's law. When the dipole-dipole array is deployed, you have a pair of current and a pair of potential electrodes that can record resistivity data at different locations and depths by shifting the electrodes horizontally and by changing the electrode spacing and dipole spacing. With the modern resistivity systems, this process is pretty much automated. And for example, if you deploy a 168 channel system, it can automatically collect over 3,000 data points in about 3 hours. And that's not including the setup time and breakdown time. Then the data processed with advanced 2D or 3D inversion algorithms. And resistivity, like density, is an intrinsic property of material and is mostly a function of lithology, porosity, clay content, permeability, fluid saturation, and fluid salinity. But when we deal with karst, most of the time we look uh, more at lithology, clay content, and fluid saturation, which is usually fresh water. Then a 2D resistivity profile can be transformed into a realistic 2D geological model, and your model would be more reliable if you have external constraints. And this could be additional geophysical data sets, or it could be ground truth data in the form of borehole control. Here's one of the acquired 2D ERT profiles at the site. Interpreted top of rock correlates well with the 125 ohm meter contour interval, marked here as a solid white line, except in areas where shallow rock is anomalously moist. The intertroch is characterized by resistivity values of about 900 ohm meters and higher. Several prominent seepage pathways in areas around the perimeter of the fly ash deposits were identified, Uh, the data I'm showing you here today is just a portion of the largest study. We actually acquired data to the north and to the south of the landfill site. Here we have a few profiles to the west and to the east of the structure. So moisture that ultimately seeps into the bedrock is controlled to a significant extent by the identified near vertical seepage zones. And remember, we discussed the joint sets in the area, and they're near vertical. And these seepage pathways are also controlled by surface topography and by locations of roads, berms, and drainage ditches. Here are all 12 interpreted resistivity profiles side by side. These vertical anomalously low resistivity zones, shown here as blue, could be interpreted as solution widening joints or other karst features. And if you don't have any other information, you could possibly interpret this as a clay infill solution widening joints. But by looking at the topography, surface features that control the runoff direction, some understanding of the hydrology, acquisition of additional geophysical data, makes it evident that these vertical anomalously low resistivity zones are just increased moisture content seeping into the near vertical fractures and joints in the bedrock. Um, if we look closer at some of the resistivity profiles, for example, profile number 9 and profile number 10 and 11, on the right hand side, there is elevation mark 360 meters. It's interesting to know that overall values below that elevation are lower. And later, it was found from a chemical analysis of the core samples that there's a different lithological unit at the depth that is apparently more susceptible to weathering and as a result has um, high moisture content due to increased permeability. So the main idea of this slide and the previous one, that when you deal with the resistivity data in karst terrain, you have to be very careful. If I would see this profile without, or these profiles without knowing any additional information where data were acquired, I would say, well, it does appear these linear features and they are likely solution widening joints and possibly clay infill. But again, once you look at the topography and other factors, it will become evident that it's just increased moisture content in fractured bedrock. So superposing 2D ERT results on the map helps with the interpretation. I'm sure many of you do use Google Earth. That's one of my favorite software packages. Another one I use is Surfer by Golden Software. But there are a lot of advanced visualization software packages. Often you have to pay a premium for those. But they do all same thing. They help you with the visualization and interpretation of your data. So looking at the ERT um, profiles side by side and the topography at the same time, we could see a strong correlation between low resistivity zones. For example, let's take this section of the data. So the blue is seepage, increased moisture content. This is a slope facing west, and when the water runoff happens during rain events, the water rolls on the slope to the west in this case, and because there's a road that acts as a natural barrier on the path, the water accumulates a little more here, and it seeps through the soil and then into the rock. So the horizontal seepage pathways are controlled by mainly topography. And in this case, at this site, the topography is almost 100% man-made. So this is entire structure is elevated. This is an active portion of the landfill that is being used, and the northern section is capped. So it's basically grass over a hill that is about 40 meters tall, and the water runs off to the west, to the east, and to the north. There's a berm here that prevents water draining or running off south to make sure this slope is stable. And at some point, when this section will be fully complete, all the deposits will be in place. It will be also kept, and the grass will be seated on top of it. And the water will be running probably to the west, to the east, to the north, and to the south. So based on the findings in this survey, we concluded that the area immediately adjacent to the landfill is not underlain by karst features that could potentially compromise integrity of the landfill. Again, this goes back to the interpretation of the data. If you don't have any additional data, you can come up with 10 different interpretations, and all of them will be right without additional data sets to some degree. So we need to make sure that the interpretation is reasonable for a particular site. Runoff from the landfill seeps into the subsurface as it flows away from the toe of the structure. Several prominent seepage pathways in areas around the perimeter of the fly ash deposits were identified. In this case, we're talking about the western side and the eastern side only, but the data were part also to the north and to the south. Moisture that ultimately seeps into bedrock is controlled to a significant extent by the identified near vertical seepage zones. And those zones are controlled again by the preferential orientation of the joint sets and the fractures for a particular lithological unit. And in this case, we have Burlington Kirkuk limestone with joints that are near vertical. Seepage pathways are controlled by surface topography and by the locations of roads, berms, and drainage ditches. In this case, all these features are man-made, and in some instances, the water is derived where it needs to go away from the structure. So in some ways, these pathways are controlled on purpose, and some are just controlled because of the uh, built roads around the site. The most prominent in terms of estimated volume of moisture content seepage pathways through the pervasively fractured bedrock were identified on the ERT profiles closest to the toe of the landfill. So if you look side by side on the resistivity profiles, you will notice that there's more um, moisture closer to the toe, and it makes sense because when the water runs off, it flows horizontally and vertically. And the further away you go from the toe, the more dispersion of the water you have. So it flows horizontally and vertically. And this is what I have to share with you today. Thank you for your attention, and let